Thank you, Professor Ng, and ladies and gentlemen, welcome to our afternoon session. My name is Reynold Cheng, and I'm a professor from Computer Science of Hong Kong U. Today, I would like to share with you some of our recent research work in graph analytics using the so-called metapaths and metastructures and its applications. Okay. So to just give you a brief background about myself, I graduated from Hong Kong U, and then I did my PhD in Purdue. Then I started as an assistant professor in Hong Kong Poly U before joining Hong Kong U. My main research is in database management, graph database analytics, and uncertainty management. Okay. So these are some of my awards. And today I would like to talk about the importance of graphs, right? And why we are interested in it. So you know, a so-called graph is essentially a network which connects different things together. Okay? Just like Facebook is a large graph because it is a social network connecting different users together based on their friendship and shared interest. And in addition, there are something called the knowledge base, okay, which essentially is a large graph by itself, which connects different kinds of things together, such as the different knowledge, okay, and their relationships. Okay. And another very interesting graph, okay, that is extensively used these days is the so-called user item purchase graph, which connects different users and the items that they have bought together. And collectively speaking, okay, all these different kinds of graphs, okay, they are generating a lot of knowledge, capturing in particular the relationships between different kinds of entities. And they're very worth investigated because they provide a rich source of information for knowledge discovery. And in this talk, I will collectively call this kind of graphs a so-called heterogeneous information network, or HIN. So why do I call it this? Because in fact, okay, HIN is a very rich graph which consists of different kinds of nodes, labels connected to each other with different kinds of relationships. For example, let us consider Imdb, which is a movie database, and it depicts a lot of different kinds of relationships between movies, actors, directors, and things like that. For example, if you look at this graph, you can see that okay, Forrest Gump, okay, and Tom Cruise, okay, is a kind of movies and actors, respectively. Okay, and these different edges, okay, in the graph can connect these different people and the movies together. And in addition, you can also see that these graphs, okay, and the edges are colored differently, meaning that they have different meanings. For example, okay, a link comic, okay, connects producer and movie together, meaning that the producer, as a node in this HIN, makes a movie, okay, or an actor, okay, could also act in the movie. So that is why there is an act link between the actor and the movie. And in fact, okay, in our TCL project, which I will share with you later, we are also building a similar movie HIN, but with a larger scale. Just to give you another example of HIN. So this is a so-called bibliographical network HIN, right, which tells you about different kinds of authors, okay, and how they are connected to different papers and venues. For example, okay, KDD is a well-known venue in knowledge discovery, okay, and Zhao Weihan is a very famous author, okay. So they are represented as a node, okay, in a HIN, okay, but each of them means different things. One of them means venue, and the other one means the author. And the authors and the venues, okay, or different kinds of nodes can be connected with different kinds of links. For example, okay, as you can see here, okay, the authors can have the red link, meaning that okay, they are the authoring or publishing these papers. Okay, and the black link between the venue, okay, and the paper name represents where is the paper published. Okay, and here I also want to illustrate another kind of HIN, which is used for elderly care in my project. Okay, so in this HIN, okay, I designed this HIN to be a graph which connects different kinds of users and the elders together. So as you can see, for example, Daisy here is an elder. So she is also providing nursing activity for Ken. Okay, so that is why okay there is a nursing link between Daisy and Ken. So all these relationships which captures the helpers and the elders could be mapped in this HIN. And we have used this HIN to provide intelligent recommendations for helpers to elders in our elderly care project called HIN Care. And we also develop a mobile application with this HIN driving the recommendation algorithm for providing recommendations to elders. Okay, so in fact, there is a lot of interest in HIN. Okay, for example, okay, HIN have been found to be very useful to study how can we predict the link or the relationships between different users. Okay, and entity profiling, okay, is another way to make use of the HIN. Okay, which sets, okay, how different entities, okay, can be enriched with the information around it by considering its relationship with other nodes in the graph. And data integration is also another interesting topic, which talks about, let's say you have different sources of data in terms of the HIN. How can you connect and integrate these different kind of HIN together to become a bigger HIN? And in fact, recently, we have also studied how to use existing HIN to provide the so-called query recommendation. The query recommendation is a very interesting and important topic because when you are using search engines such as Google, when you type your keywords into the text box, you could automatically see that a number of provided suggestions to you. So these suggestions, okay, actually come from the HIN, and we study how the HIN can be used to give good suggestions of the queries to the users while you are typing your query. Okay, so I have given a number of examples for the HIN and also their applications. But one fundamental question, okay, that we need to answer is how can we use this HIN to measure the closeness between two entities or nodes? So we call this a relevance computation problem. Okay, so to give you an example, okay, the HIN here, okay, shows different people in the US, okay, and the political leaders in the US and the different relationships. For example, okay, Barack Obama was a former president, and he was actually a US president, a writer, a leader, and a person, okay? So the tree on the above tells us about the taxonomy or the hierarchical relationships, different concepts that describe Obama. And also, Obama, okay, has a child, of course, okay, so that is why, okay, he has child relationship with one of his daughters, okay, and he's also the citizen of US, okay. And in computer science, what we are always interested to know is how can we measure the closeness between two nodes, okay. So, for example, how can we make use of this HIN structure to help us to understand how Barack Obama is relevant to George Bush, okay? Meaning that can we measure the distance between Barack Obama and George Bush by measuring the relationships in terms of the HIN, right? Now, in order to measure the closeness or the relevance between the two nodes effectively, right, people have developed something called Metapath, which is also the topic of our talk today. So what is a Metapath? Actually, Metapath is a very interesting but easy concept. Essentially, it is just a sequence of node classes connecting different edges together. Okay? So for example, okay, here we can say that Barack Obama, okay, is related to Michelle Obama because, okay, they both have a child. Okay? So we can try to reach Michelle Obama from Barack Obama following this Metapath, saying that he is a US president and has a child, okay, a shared child, okay, with US First Lady, where we follow the link has child, and then here has child -1 means that we reverse the direction, right? So that means Barack Obama can go through MA Obama to reach Michelle Obama. Okay, and this kind of metapath, okay, just one example. There are other kinds of metapaths which could connect the US presidents and the US First Lady in different ways. Okay, and the interesting thing about the metapaths is that they capture some important relationships between the two nodes, which allows us to define the relevance or closeness between the two nodes. So one way to do this is to use the so-called path count, okay, or what I call PC, okay. Path count simply means how many metapaths can be used to reach from one source to the one target. For example, Barack Obama and Michelle Obama can be reached by using this metapath twice, okay, saying that the US president and first lady has a common child, but because they have two daughters, so that is why we say that the PC between these two nodes is 2. Okay? But this obviously may not be the best way because there may be sometimes the metapath, okay, will bias towards the popular objects with a lot of links. So that is why, okay, a better way may be to use the so-called the concept of random walk to measure the similarity between the two nodes using the metapaths. Okay? So for example, okay, with the metapath, okay, person and the same person has the same child, okay, then okay, there is a chance that Barack Obama can reach Michelle Obama with a probability of 0.5 following the random walk here. Okay, so I don't want to talk about the details, but basically the random walk is just the probability that a node can reach another node. Okay, and in fact, okay, there are a lot of the so-called similarity or relevance measures based on metapaths. Okay, so in the last 10 years or so I'm not going to give all the details. Okay, but okay, what I want to share with you is one of the problems that we study about how do we find metapaths for which these similarity measures need to operate on. Without the metapath knowledge, these metapath-based measures cannot actually compute. So it is important to find the most important metapaths for us to make use of these similarity measures. So in our publications like a few years ago, okay, we tried to discover solutions that can help us to find the best metapaths and also learn the weighting functions between the two nodes based on these metapaths. Okay, so let me give you the main idea. Okay, so here in our framework, okay, we have a number of so-called example node pairs which the user provides to us. For example, the user can set that Barack Obama and Michelle Obama are example pairs, right? And Bill Clinton and Hillary Clinton are another example pairs. And what our so-called metapath generation module does is, given the examples you tell me, together with the HIN, I want to try to find out what are the metapaths that can be the most important ones to describe the relationships between these pairs. Okay? So in this case, for example, I may find that there are two metapaths that are the most important to describe Barack Obama and Michelle Obama, as well as Bill Clinton and Hillary Clinton, because they both have child, okay? And also at the same time, the president and the first lady belongs to the same political party. Okay? So that is the main idea. Give you some example pairs, find the metapaths which indicates the most important relationship between them. And once we find these important relationships can be used in the relevance score computations between the node pairs. Okay? But because of the large scale of this problem, due to the fact that there are such a large number of metapaths, so that is why, right, in our paper, we developed a solution called forward stage-wise path generation, or FSPG, which essentially use a machine learning approach to try to find the best fit metapaths to describe the examples. Okay, and we have also developed a data structure called greedy tree to support the speed up of the finding of the best metapaths according to a machine model training module. Okay, so I will skip the details here, but instead just give you an experimental result. Okay, so in this experiment, we have used Yago, which is quite a large HIN with 2.1 million nodes. And what we are trying to do is to try to study how metapaths can be used in link prediction. Okay. So the FSPG in this figure is our approach, and we compare FSPG with the existing ones, okay, in which the metapaths are known, okay, and input by the user with a different length. Okay, but in our approach, okay, we don't. In our approach, our goal is to discover the metapaths. So we can find that we achieved the best AUC rate, okay? And in particular, if you look at the figure on the right, our method is able to discover some interesting metapaths, okay? From short length metapaths, such as saying that the person lives in a country, to some more complicated one, like the one in the bottom, saying that the person, okay, is predicted, okay, to be a citizen of a country if it is born in a city, okay, in which the event, okay, also happens between the city and the country. So what we find is that in our study, okay, metapaths of different lengths can also play important roles. And the weight, okay, as we see in the right of the figure here, which indicates the importance of finding nodes that are similar to each other. Okay, so now let me play a short video about how we make use of this so-called example node pair-based approach to find metapaths and implement it in a real solution for search. Okay, so we call this a query by example search, or QBE search. Okay, so here, okay, what the user can do is, first of all, he inputs a keyword, for example, Obama, okay, and then based on that, okay, the user will also select some of the properties he want to do the search, okay. So, for example, okay, the user indicates that he want to search something for Obama, okay. So our search engine will display, okay, a number of names, okay, corresponding to the US president, okay, based on the search keyword Obama, okay, and then if we continue the example, okay, we also want to find a number of US first ladies, okay. So after that, okay, a number of names, okay, will be put into the pool. So now, okay, is the way what we want to do is we want to compose a number of example pairs from this list of names, okay. So here you can see that there is a source and the target here, okay. So we can see that we are trying to build the relationship between Bill Clinton, Hillary Clinton, Barack Obama, his wife, and George and his wife, okay. So we are interested to try to find out more relationships, okay. So that is why we call this a node pair examples, okay. Here we indicate 3 examples here, and without writing complex queries, we want to find out some more interesting relationships, okay. So after a while, okay, our search engine will return a number of metapaths, okay, which tells you that based on these 3 examples, these are the metapaths out of many, that these are the 3 metapaths that are distinctively important to characterize the relationships between these node examples, okay. So once this is done, okay, these metapaths are used to find out some more suggestions. So in this case, where you can find out more presidents and first ladies, okay, based on the 3 examples that we have given, okay. And the good thing about this approach is that the user doesn't have to type anything, but just track the names, okay. He doesn't need to indicate and specify the query that he wants to do, okay. So I skipped some details here, okay, but I hope you get the main idea, okay. So next, okay, I want to talk about a recent development, okay, and a finding that actually is, although the metapaths could be used to provide a useful link between the 2 nodes, sometimes they do have defects or limitation, okay, in the sense that, okay, sometimes they cannot represent some more complex relationship, okay. So if we look at this example, suppose that, okay, in this bibliographic database, okay, we have a number of authors and the papers, okay, and suppose I want to find out researchers, okay, who have published papers in the same conference venue and also the same topic with his papers, okay. So let's say, okay, here there are the 3 researchers, okay, in data mining, okay, and they have published some papers, okay, in certain venues, okay. And suppose we want to retrieve, okay, those pairs of all the researchers who have the closest relationship, okay. And we can see that the first author, okay, Cheng, and the second author, Hang, okay, they publish papers which appear in both KDD, and also they have the keyword mining in the paper. Okay. However, okay, if we compare another pair, okay, Jiawei and Yang Chang, okay, although they also publish papers, but they seldom meet the conditions that the papers are about the same topic and also appear in the same conference. Okay, so we would try to say that, okay, the first two authors are closer in the relationship than the second and the third pair. However, okay, if the Metapath similarity measure, it fails to capture this because, okay, we can only see that, okay, the authors are related to authors, okay, if they are connected to the same value through their papers. Another Metapath is the two authors, they publish the papers in the same, with the same topic, okay? So if we run the similarity measure, we will find that all the Metapath measures show that A1, A2, okay, have the same score as A2 and A3. So what we really want is something that can capture the more complex relationship between the two authors, okay? Saying that the two authors publish the same papers, sorry, the two authors publish two papers, but they have to both satisfy the fact that they are about the same topic and same value before we consider them to be close enough, okay? However, the Metapath is just a linear structure. It doesn't have any branches as we shown in this diagram. So that is why sometimes the Metapaths fail to capture some close relationship between two nodes. And we call this nonlinear structure a meta structure, nonlinear Metapath structure as meta structure. Okay? And what we did, okay, in our KDD work is that, okay, we extend the Metapath similarity measures to meta structure by, first of all, okay, extending the path counts, which I mentioned some minutes ago, to structure count, which counts the number of meta structures between two nodes. And we also extend our random walk measures for Metapaths to random walk based on meta structures. Okay, and as a result, we come up with this table which said how Metapath measures can be extended to meta structures. Okay, and I'll skip the details, but again, okay, let me show you the results. Okay, so we applied this technique to entity resolution. Okay, so you know, in an HIN, okay, as I will also tell you later, that actually there are a lot of duplicated entities. Okay, so for example, in Yago, one of the very famous HIN, we find that Barack Obama is a node, presidency of Barack Obama is another node in HIN. Okay, so what we want to do is we want to identify these nodes actually which are identical, okay, based on the use of Metapath or metastructure similarity. Okay, and in this experiment, okay, we compare the Metapaths, okay, which says that if P1 and P2 they're married to the same person, then P1 and P2 are the same person. Okay, this is a Metapath. Okay, another Metapath says that P1 and P2 they are the same person if they are affiliated to the same organization. Okay, a metastructure combine these two Metapaths, okay, to impose a more stringent constraint, saying that P1 and P2 are the same person if they get married to the same person and they are also affiliated to the same organization. Okay, so in our experiment, okay, what we find is that with the use of the metastructure, as we see in this table below, they achieve the highest score, okay, in terms of the AUC score, which measures how accurate we are in identifying the duplicated entities. Okay, so these experiments show that the metastructure, which captures the more complex relationship between the two nodes, are indeed able to identify duplicate pairs. Okay, so with a few minutes left, okay, I want to briefly also talk about our recent work with TCL. Okay, so in fact, TCL is very generous to support our project. Okay, which make use of HIN to do recommendation. So in particular, okay, what we are interested is the following question. So suppose that we have an online movie platform, okay, So whether it is possible for the platform to intelligently suggest movies for me, okay, based on my browsing history, based on what I have watched before, okay? And the second question is, okay, suppose that I have input some of my queries about the movies I want. Can I use this online movie platform to also develop some kind of suggestions or suggested query that would be useful for my search? Okay, so in order to answer this question, okay, we could make use of some of the techniques that I mentioned earlier. But also the first hurdle that we need to overcome, okay, is that we have to build a large HIN consisting of the movie information so that we can do the search. Okay. However, okay, this is not particularly easy because building a movie HIN, okay, from scratch, okay, means that, okay, we have to first of all look at what are there in the what are the data that can be given to us, okay? And luckily, okay, we find a movie database from something called Falcon, okay? And the database is a very large database containing Chinese and Western movies from 1930 to 2020. So a lot of movies, okay? More than 140K movies from 100 countries, 150,000 actors, 40,000 directors, and 170 tags or labels. Okay, and moreover, okay, they have already put this information from different vendors such as Tencent, ETE, Youku. Okay, a large number of vendors give their information to this open database. Okay. So from this database, our task is to construct an HIN for which you can do recommendation and analysis. And after some search from the literature, okay, we have adopted data schema, okay, or HIN schema, okay, given by this paper, okay, in which you can see that this schema, okay, is quite simple. It consists of a number of labels. Okay, a number of labels according to whether they're actors, company, okay, decade, director, and also all the links. Okay, as we said in HIN, all the links have their own meanings. So these links, for example, consist of whether the starring, directed by, okay, produced by, different kinds of links. Okay, and to show you an example here, okay, we have a screenshot, okay, about the HIN that we have built so far. Okay. So excuse me if they are not in English, because really we have been doing a hard job in combining the different Chinese and Western movies together. Okay, so that is why sometimes these notes are represented by the Chinese. Okay, but basically, okay, what this snapshot is showing is the different kinds of notes represent the concepts. They are connected to each other. For example, these are all the movies and all the information. Okay, telling you about what are the movies starred by this Miranda Hart. Okay, so this looks great, right? But in fact, we face a lot of problems and we are still solving it now. Okay, one of the main problems is because these movie names, okay, as I said before, they are contributed by 7 vendors. So as you can see here, okay, different movies, because of the different versions they are published, different countries or places they are published, they have different names. Even for Harry Potter and the Prisoner of Azkaban, for example, okay, you can see that there are 4 different Chinese translations. Okay, sometimes they look similar, sometimes they could be a little bit different. Okay, so another example is this Brotherhood of Blaze 1. Okay, but you see that, okay, don't know why. Okay, in the Chinese title they have 2. Okay, so but in fact they belong to the same movie. Okay, it's just that they have the different publishers and they give you different names. So it is important for us to resolve these duplications so that we don't mess the HIN and give us a poor recommendation. Okay, so this is another example. Not just the movie names, but actually actor names also have problem because, again, due to the Chinese translations. Okay, this Mark Ruffalo, for example, they have 2 different similar Chinese translations. Okay, so this makes things difficult because now you are talking about an HIN consisting of millions of entities, okay? And the actor names, movie names, actually they are duplicates. So how can we detect this? So what we have to do is, first of all, we have to clean up this HIN before we can do anything. Okay, and we call this deduplication. Okay, deduplication, okay, is a must. Okay, in my opinion. Okay, because if we don't do these deduplications, okay, it will be very hard. Okay, for the HIN to do its job in recommendation. So what we have to do is that we have to look at this HIN again. Okay, and try to study what are the different titles, actors, directors, and the movie descriptions, and try to see whether we can resolve these deduplication problems. So we have been using a number of techniques, such as skipgram and jacket distance, to measure the similarity between the two NUC strings. Okay, and we have also been using some more advanced methods, such as this so-called entity alignment methods, in order to find out whether two NUCs in the HIN are actually the same based on their structure in the graph. Okay, and we are also considering to use the NLP techniques to resolve these duplications. Okay, and our recent results have been quite, I cannot say totally successful, but at least, okay, we have removed 2,000 duplicated movie entities from the database. Okay. And to summarize, okay, what we are trying to do next, actually, we are already studying, is to try to see how we can make use of the HIN that we have constructed and also the metapaths, okay, in order to do recommendations of movies to users. In fact, okay, for this problem, okay, recently a few works have been using metapaths already, and the main idea is they compute the similarity between users and items. Items here means could be products, could be movies. Okay, use metapath-based measures to compute the similarity, and then incorporate this knowledge into graph regularizations, matrix factorizations, and GNN techniques. So, given this background, okay, what we think, okay, would be a good direction is to try to think about how we can discover the best metapaths and metastructures for effective recommendation. Because in most of these works, okay, metapaths are assumed to be given. But okay, in our experience, with the building of the HIN for the video, we know that finding even the good metapaths to start with is very difficult. Okay? So what we are trying to do now is to try to see whether we could develop some novel metapath discovery algorithms so that we can make use of them to do our recommendation. Okay, so we didn't get a lot of results yet. Okay, but a preliminary study, okay, in the previous work showed that this is an important problem. Okay, so don't worry about this table. Okay, what you need to know is that there is a certain algorithm, okay, which is based on metapath using a PEA stage, and the authors have done some experiments to test what if some metapaths are removed. What will this affect the recommendation results? And we find that for some of the metapaths that are very crucial, if they're removed, then the effectiveness will drop by as many as 46%. Okay, so this shows metapaths are very, very important in doing recommendation, and we have to choose the right set of that. Okay, so I think I hope I just finished in time. Okay, and many thanks for being with me in the last 30 minutes. So if you have any questions, please feel free to send an email to me. Okay, I will be very happy to answer you. Thank you very much.